Okay, lecture 8, Eulers method. So we'll summarize what we've done so far, and then we will talk about Eulers method. So we've dealt with some first order equations graphically. If we have dy dt equals f of ty, you can get slope fields and trace solution curves. Analytically, let me change the view on this so I can actually see what I'm doing. There we go. Analytically, you can do separation of variables. We haven't seen integrating factors or undetermined coefficients. Oh yeah, we saw those last week. And then these analytic methods handle certain types of differential equations. We want to use slope fields to build a numerical method to approximate solutions, which allows us to solve equations that can't be solved analytically. So generally, these kinds of equations here, if we want to solve them, this has to be of a particular form. Otherwise, it's just a little bit difficult. So we do numerical analysis for this. So dy dt equals y over 10, 10 minus y. So draw the slope field. How do you draw the slope field? Step 1, set the right-hand side equal to 0 to find the equilibria. Hopefully everybody writes that down because it's important to remember how to find the equilibria. So y over 10, 10 minus y equals 0 means that y equals 0 or y equals 10. So those are equilibria. 2, sketching a graph, sketching a slope field. So we'll draw first off the equilibria. So y equals 0, this is one equilibria here, and y equals 10 is the other one. So those are our equilibria. This is my t-axis, this is my y-axis. Third is find the sign of y prime. So y prime is y over 10 times 10 minus y. If we take a test point, say 20, we get 20 over 10 times 10 minus 20, that's less than 0. So that means y prime is less than 0 if we're above y equals 10. So going down. If we take, say, y equal to 5, that gives us 5 over 10 times 10 minus 5, and that's greater than 0. Y equals 5 is here, and that's got a positive slope. So everywhere between the equilibria, we have a positive slope, because the slope can only change signs when you go across the equilibria. And then if we take y equals, say, minus 10, that gives us minus 10 over 10 times minus 10, times 10 minus minus 10, which is less than 0 because this is negative, but this is all positive. And so our slopes here are also negative. So that's what the slope field looks like. And if we take the solution curve with y of 0 equals 1, that means we're starting here, t equals 0, y equals 1, and our slope curve will look, our solution curve will look like this. If I could draw better. So we can figure out what the curve looks like. We don't have a formula for it. So question that comes up is, what's y of 2? So we want to estimate y of 2 to within 0.1 and do a version by hand first and illustrate with Excel and GeoGebra. So we're starting here at y equals 1. And if we follow the slopes, we end up somewhere over here by the time we get to y equals 2. And I want to know, what is that y value? Right? It's up here to the right somewhere, but I don't know what it is. So this is the slope field. Here's my y equals 0 equilibria. and then y equals 10 equilibria somewhere off the top. Okay, so how do I want to estimate this? Well, what do I know about this thing? Well, I know a point and I know a slope. So if I just take that slope and follow the line that slope has for 1 unit, I'll end up here. And that has got a slope. And if I take that slope and follow that line for 1 unit, oh, sorry, we actually want to end up here somewhere. That's y equals 2. I'll end up over here somewhere. Right, so what we're going to do is pick a point. We know a slope, so you can draw a line segment, follow this line segment for delta t equals to 1. Stop. You're now at a new point with a new slope. Follow that slope for 1 time period and see where you are. So how does this work? So we'll set up a little table. Did I set up the table down here? No, it's okay. So old point, slope m, delta t, delta y. I have to move this out of the way so I can see what I'm doing. And new point. So old point, that's where we started from. We started at 0, 1. M, that's slope, which is the same thing as the derivative in this case, dy dt, equals y over 10 times 10 minus y. So if we plug in y equals 0, y equals 1, sorry about that, we get 1 over 10 times 10 minus 1 equals 0.9. So my slope at that point, at my old point, is 0.9. Changing t, we're just going to go 1 step to the right. So 1 unit to the right. So how far up do I go? So if my slope here, m equals 0.9, delta t equals 1, then what's delta y? Well, we know what the relationship between slope, delta t, and delta y is. Delta y is just m times delta t, right? Because that's how slope is defined. So .9 times 1 is 0.9. So what's my new point? Well, I changed t by 1, so I take 0 plus 1 and update my t position. Started at 1, added a delta y of 0.9, so that means I'm now at 1.9. So that's my new point. So that's this point here, 1, 1.9. So we want to update that point. There's my m. Oh, this is my new point that I'm at. 1.9. Oops, sorry about that. Okay, so what's our new slope at this point? We plug in y equals 1.9, we get 1.9 over 10 times 10 minus 1.9. That should give us 1.529, I think. So that's my slope at this point. And we want delta t is 1 because we're going to go 1 step to the right. And how far up do we go? Well, m times delta t, slope times change in slope times run equals rise, right? So we go up 1.529. So my new point is we started at 1, we added 1, that gives me 2. 1.9 plus 1.529 gives me 3.43. About 3.429. So that's this number plus the 1.9. Great. So that's what this point is. This is 3.429. So is that actually equal to what the function is? We've approximated, but is that actually equal to what the function is? So how can we tell what the function is? Well, we can go to GeoGebra and actually graph this thing. Where's my GeoGebra? There we go. Okay, so there's the GeoGebra. So this is the slope field that's been put in. We'll zoom in a little bit. So we're starting at 0, 1. What we want is to solve an ODE with an initial condition. Oh, man, I've been having issues with that all day. Solve ODE. And the ODE we want to solve for the right-hand side is y over 10 times, oops, what's that parentheses? Times 10 minus y. And then the point we want to start at is 0, 1. And it thinks a little bit, and there it is. So there's the curve. There's our initial condition. There's the solution. We want to know what's f of 2. When t equals 2, what's the function? So f of 2 is about 4.51. We can plot that. Right, there's my f of 2. So there's the curve. And this point A here, that's f of 2. And we want to know, we want to be able to approximate that. And GeoGebra can approximate it. And how does it do it? Well, we does it basically how we've using things like Euler's method, but a little bit more complicated. Geez, what's going on there? So there's B, our initial condition, solution curve, and it hits A there. Note that it's tangent everywhere. Great. So let me shift the screen a little bit, and we'll look at Excel. And Excel is nice because it's easy to actually program in what Excel is. So what we did is we started at 0. We went to 1. What's our slope? The slope is the right-hand side of the equation. So it's going to be equal to y over 10, so y1 divided by 10 times 10 minus 1. So there's our 0.19 slope. That should be 0.9, I think. Okay, I changed that so that the formula is actually correct. Change in t was 1. Change in y then is slope times change in t. So that equals this times that, which is 0.9. What's your new t? It's the old t, shift plus 1, because that's our change in t. And our new y is the old y plus the change in y. Right? And then we can update everything. The old t is now the new t. And we update that old y to be the new y. Great. And so with that, we can just have Excel. So Control D is the command for just fill everything down. And that gives us our 3.439. Right, 3.439. That's not so good, right? We saw from GeoGebra that the actual answer we want is about 4.5. So it's not a very good estimate, but I can always change the step size to make it smaller. Right, so 2 steps of size 0.1 in t. That takes me from 0 to 0.2. but maybe it'll actually help me when I get to, by updating more often, perhaps by the time I get to 2, I will have a better estimate. So Control D, bring all that down. So here we are at 2, 4.38. So that's closer, right? 4.38, that's a better approximation. And we did that by taking smaller and smaller step sizes on Y. So suppose we wanted to actually to be within 0.0, if we want to be really close, how would we actually get there? So if we say, let's change this to 0.01, and change all the numbers around. Well, that only gets you to 0.2, because if each step size is 0.01, if you take 20 step sizes, you're going to get to 0.2. So we need a lot more step sizes to be able to estimate what 2 is. So let's go down, say to 200 and some, and see how that works out. There we go. So 4.49, right? Much better. That's much closer to the 4.5 that we're actually looking for. So if we make the step size smaller, right? If we change the step size to 0.01, then the estimate works better. But the thing is that, you know, if the step size is smaller, you're going to have lots more steps. You have to take many more steps because they're shorter to be able to cover that distance of 2. Right? So you end up having to take 200 steps to go 2 units, but you get a much better approximation. So, oops, sorry about that. Let me bring back up the lecture notes. So what's the idea here? We started at a point t equals 0, y equals 1. There's a slope there of, what was the slope? It was 0.9. Was it 1.9? It was 0.9. Slope equals 0.9. So if we've got a point and a slope, that means we can draw the line through there, and we can mark off a certain distance, say delta t, and then this is delta y, and that's m times delta t. And that brings us to a new point. And what's the new point? The new point is the old point, which is 0 plus whatever delta t is, and then y equals 1 plus whatever our delta y is. And at this new point, because we're on a slope field, we know that there's a slope there. And so we can just calculate this again using our new y, and that gives us another slope. And then you can just repeat it. This is called the step size. The bigger you make it, the worse the error, but the shorter the computation time. The smaller that you make it, the less the error, but the longer the computation time. Then you get a larger number of steps that you have to do. So what we want to do then is, for this, is we want to be able to, what we did when we had 0.1, we had lots and lots of little steps, and it was able to follow the turn in the curve pretty well, although it ended up being a little bit behind it. This approximation, which had a step size of 1, just starts here, goes to here. From there, it just goes up to here, one big step, and you have a big gap there. So we're not going to do a huge amount with numerical analysis in here, but figuring out where following trajectories by doing these kinds of approximations is a really standard way to figure out what the values are of solution curves at various places. What happens if the step size becomes too large? I'm not actually going to demonstrate with GeoGebra, but I am going to go to back to Excel. if I can find it. There it is. And say, well, what happens if we make the step side really big? Let's make change in t equal to, well, actually, I'm just gonna, yeah, let's make change in t equal to 4. Just run that down. I don't know. We'll do 20 steps with step size of 4. And we get overflow errors. Too big, too big. Oh, it's terrible. Terrible, terrible, terrible. What happened? Well, we started 0, 1. Slope is 0.9. The change in t is 4. So we're going to have the new t is at 4. The change in y is 4.6. Okay, that's fine. So 4 to 4.6. Slope is 2.4 at the new y. Change in 4. So change in y is now 9.936. So that makes our new t 8 and our new y is 14. What that means is that we jumped over the equilibrium at 10. And so if we look at a t of 8 and a y of 14, you plug that in, you get minus 6.59, multiply that by 4, you get minus 26. And now we jumped over the both equilibrium, and now we're on the negative side, and everything goes berserk. Overflow, overflow, overflow. So what's going on there? Let's draw a picture to see what's going on there. So what we have is our slope field. Which is basically like this. Y equals 10, y equals 0. Everything here is negative. Everything in here is positive. But keep in mind that as we get closer and closer to the equilibria, the slopes get shallower and shallower. Same thing here, the slopes are shallow near the equilibria, but steep away from it. So if we start at 0, 1, and we make a step size of 4 with our slope, we'll end up here. And if we make another step size of 4 with the slope, we calculate our slope, we get something here. Then we ended up here somewhere, and we actually crossed over the equilibrium 10, and we ended up far enough up here where the slopes are pretty steep. So when we tried to do our next batch of Eulers method, delta t is 4, but our slope here is pretty steep. So ended up down here. And once you end up down here, you're just screwed, right? Because you just go down to minus infinity. So when you're doing numerical analysis, it's important to have a feel for what the solution curves look like, right? Knowing where the equilibria are allows you to choose a step size, which is effective for Eulers method. A step size of 4 here just blows everything up and it doesn't work very well. We can do the same thing here, or this method for the equation dy dt equals y plus t with the initial condition of y minus 4 equals 3.1. So let me just count these. So changing y. Okay, so this is my old point, slope, m equals y plus t, delta y, new point. So what does this end up? We started at minus 4, 3.1. My slope then at that point, we plug in minus 4 and 3.1 into y plus t. That equals 0.9. Delta t, we're taking a step size of 1. So delta y is 1 times minus 0.9. And remember, delta y is always m delta t because it's a slope, minus 0.9. So our new point is minus 3, right? Minus 4 plus 1 is minus 3. 3.1 plus minus 0.9 is 2.2. So we take the new point, we put it in as the old point, and run it through again. So the slope is y plus t, so minus 3 plus 2.2 is minus 0.8. Change in t is still 1, so minus 0.8 is my delta y, this times this. And now we're at minus 2, because that's 1 plus minus 3 minus 0.8 plus 2.2 is 1.6. So actually 1.4. So our new point is minus 2, 1.4. What's our slope? Minus 2 plus 1.4, because that's our right-hand side, y plus t, is minus 0.6. Delta t is 1. So minus 0.6 is delta y. And so we update that, we get minus 1, and then minus 1.6 gives me 0.8. So minus 1 comma 0.8 is our point. What's our slope there? Minus 1 plus 0.8 is minus 0.2. Delta t is 1. 1 times minus 0.2 gives me delta y as being minus 0.2. And then finally, we're at 0.6. So what's the error? How far off is that? Well, we can always check that by looking at GeoGebra again. So let's switch to GeoGebra. We're going to delete all this stuff because we're dealing with a new system. So we'll put in our slope field, and that's just x plus y, oops, plus y. Remember that GeoGebra doesn't have a t, or at least I haven't figured out how to deal with it. So here's our slope field. Remember that we've seen this slope field before earlier in the course. Minus x minus 1 was a straight line solution to this. Right? So there's our straight line solution. Our initial condition, we're solving x plus y is our field, and the point we're starting at is minus 4 comma 3.1. And there's our equation. Great. So let's put in our starting point, minus 4 comma 3. Minus 4 comma 3.1. There's our initial condition A. What is g of 0? Because that's what we're trying to approximate. And it's 4.49 something, something, something. So that's the point B that we're trying to approximate. But our approximation from Euler's method was 0, 0.6. And it's way down there. So why is our approximation so bad? And the answer is that the curve, the red curve, turned, right? And Euler's method doesn't keep up with that. So the first point on Euler's method was minus 3.2, which is that point. So we followed the slope at A for 1 unit to the right, and we ended up at D. And then the next point we got to was minus 2, 1.4. Right? We followed the slope at D, 1 unit to the right, and that got us to E. And we calculated the slope at E. And E is minus 1. We calculated the slope at E and followed that for 1 unit. And we ended up at F, and then we went down to C. So what Euler's method is doing then is you pick a point and you follow the slope till for 1 unit to the right, or whatever your step size is. And that's your first approximation. And then you update at that point, go 1 unit to the right, and that's your second approximation. But the red curve is bending, and Euler's method isn't really picking it up because we're a little bit too close still to the green curve. It isn't until we get down here at point F out to point C that Euler's method is starting to see that we're actually going up. And so there's already a gap, a huge gap between these things. So to make that method better, you're going to have to make the step size smaller so that you can go with the curve there. So again, we want to be able to, whenever you're doing numerical analysis, have an idea, a geometric picture of what it is you're actually looking at, so that you can actually know how to choose your step sizes so that it works. So, and if you look at the solution to the ODE here, you can notice that the 1/10 e to the 4th e to the x minus 1, that's our homogeneous solution. Oh no, the minus x minus 1 is the particular solution. The 1/10 e to the 4th e to the x is the homogeneous solution. And, you know, we get this straight line solution here, and it's sort of playing the role of a equilibrium, because the slopes are fairly small there, or it's fairly close to -1 there. They don't deviate from -1 much. And so you have to get away from the equilibrium before you can kind of catch up with the curve there. So let's see, go back to the notes. So don't know where I was there. This is not a particularly good estimate because our step size was too big, and because the curve's curved away from it. And you have to be a little bit careful when you're doing numerical analysis, that you have an understanding of the underlying behavior of the system before you just start plugging stuff in.